In this lesson, we shall focus on mathematics, MAT3711, real analysis, preliminaries, metric spaces, the notion of a metric on a set X as a distance function. And we proceed as follows. Okay, first things first, we shall look at the basics, the preliminaries, and we shall see how well we're able to go through these basics and make sense of them. Okay, as one would expect, we are trying to make sure that in our discussion, we actually have a full picture of the basics we need to know. Like the set of natural numbers is denoted by the letter N, capital N, 1, 2, 3 as elements. And the set of integers is denoted as shown here. The set of rational numbers becomes quotients of integers, but with denominators non-zero. So Q being given by M over N, where M and N are integers, the denominator N never zero. Otherwise, would have an undefined case. The real numbers are defined as to contain X, so that X is a real number. This was possibly a very lazy one. Okay, but however, yes, it contains real numbers, but you need to understand that the real numbers themselves are a combination of the rationals and the irrationals. So we know that. Now, to say R is a field, what does it mean to say the set of real numbers is a field? This means R is equipped with two operations. The addition operation, which is from R cross R to R, called addition. And multiplication operation. R times R would produce a real number, such that the following axioms hold. Okay, let us go through the axioms quickly in terms of what the axioms of a field are. First, A1 would be that for any x that are in x and y that are in R, the sum is in R. That is A1, axiom 1. Axiom 2, whenever x and y, whenever we have x plus y, then it is true that it is y plus x and x and y in R. So in other words, you have commutativity, but also closure under the addition property. So the first 5 axioms themselves hinge on the operation of addition, and a field as being closed under both operations of addition and multiplication. Also, if you look at the third axiom, you have associativity, right? X plus y plus z would be x plus y plus z for all the x, y, z in R. So you have commutativity, associativity, but also there exists a unique element 0 in R called 0, such that x plus 0 equals x for all x in R. For every x in R, there exists a unique element y in R, such that x plus y is 0. We denote such an element by minus x. First, we look at the sequence of the axioms that pertain addition. We mention the existence of a unique element 0, such that x plus 0 is x for all x in R. After the introduction of the unique element 0, we therefore introduce what we call a unique element that is an additive inverse under addition axiom 5, so that x plus y is 0, but this means that y is minus x. Okay. Now, there are the axioms that pertain multiplication, and these axioms, you have 5 addition axioms and 5 axioms that pertain multiplication. First, for multiplication, for any x, y in R, then the product is in R. So in other words, obviously we write xy. We write xy in the place of x times y. But this would mean that the xy itself is an element of R whenever x and y are in R. This means closure under multiplication, but also commutativity under multiplication, so that xy is yx for all xy in R. Third multiplication axiom, commutativity under addition, right? So you have x times yz in parentheses, which is xy times z for all xy z in R. But also there is distribution. Now, Okay, and you're able to see that up to the third axiom, we have the same order, and obviously we have associativity there up to M3 in the same way as A3. But if you look at M4, then you have distribution and multiplication distributes of addition from the left for all X, Y, and R, X, Y, Z, and R. Next, there exists a unique element, 1 in R, such that X times 1 is X for all X in R. For each non-zero X in R, there exists a unique element denoted by 1 over X, which is X to the minus 1, such that X times 1 over X is 1. Okay. So now there is a unique element that is 0, the neutral element in addition, but the neutral element here, which is the identity M5 and A4, the identity in M5 is 1, and then after we introduce the neutral element M5, then we have that we can introduce the multiplicative inverse in the same way that we introduce the additive inverse in A5. Okay, these become the axioms of a field, but once again, these are not examinable. Why? Because they're too basic, and this module is a bit more advanced than that. But we just mentioned them. Now, to say R is ordered means R is equipped with an order relation, less than, which satisfies the following axioms. For all X, Y, and R, either X is less than Y is less than X, or X equals Y. So in other words, the order relation 1 indicates that for any two real numbers, for all X, Y, and R, either X is less than Y. So if you have two numbers, two numbers X and Y, either X is smaller than Y, or Y is smaller than X, or they're equal. And this law is a law you might have seen before called the trichotomy law. Right, so now in the order relation 2 would be that if ever X is less than Y, then you can add Z on both sides of the inequality. Okay, so order relation 2 says that for all Z in R, whenever X is less than Y, then you can add Z both sides. If X is less than Y and 0 is less than Z, then you can multiply through by Z. But Z is positive, it's bigger than 0, so you can multiply through by it. X is less than Y. Y is less than Z. X is less than Z. This means X is less than Z for all X, Y, Z in R. Okay, so obviously this one is the order relation called transitivity. So X is less than Y and Y is less than Z. So it means that X is less than Z in that order. And this is true for all that. So X is less than Y, but Y is less than Z. Surely this means that X is less than Z. And this one is called the law of transitivity. Right, so, okay, these laws, we're just mentioning them. If X is less than Y, so that they give this some structure, the kind of structures we shall be dealing with before we continue. If X is less than Y, we also write that Y is bigger than X, which means X is less than Y still. The relation X is equal to Y, also written Y be equal to X, is defined by this. X is equal to Y, if and only if X is less than Y, or X equals Y. Given X and Y in R, either X is less or equal to Y, or X is greater or equal to Y. Prove this. The elements 0, 1 are distinct. Okay, that is 0 is not equal to 1. We'll engage with the following example. Okay, let us look at some of these basics before we move on to the kinds of things we shall be doing. But obviously, this module is about metric spaces. But before we reach the metric spaces, we discussed the notion of countability and so on, so that you can understand these kinds of states we shall be dealing with. Right, if A is an element of R, and A is non-zero, then the square of any real number that is not 0 is surely positive. Hence, this means that 1 is bigger than 0. Okay, that's fine. But pay attention to this and note what we're able to achieve here at this point. I'm wondering what I pressed here. what we're able to achieve here at this particular point. Okay, right. There are a couple of things that we need to take note of. But what is this? The essence of this, we need to prove that 1 is bigger than 0. 1 is bigger than 0. So, to prove that 1 is bigger than 0, how do you prove that 1 is bigger than 0, given that you have a squared is indeed bigger than 0, hence 1 is bigger than 0? How do you prove this? Let us discuss the proof of this. Okay. We note either that a is positive or a is negative, because a is a real number. Okay, a is positive or a is negative if a is bigger than 0, a is positive or a is negative. Why? Because it's a real number. Any real number is either positive or negative, because it is not 0. Obviously, you could say any real number is either positive or negative or 0, but it's non-zero. So in other words, we're dealing with either a number that is positive or negative. If a is positive, then by O3, which we've just seen, we'll just revert to that. And there's an exercise just make mention of, but it's not so significant. By also an exercise above, which sort of will explain why this is the case. So now we're looking at the case when a is positive. Right, if a is positive, then you can write a times a is bigger than a times 0. Okay, because we're looking at the fact that a is positive. A is positive, then you can multiply both left and right by a in this inequality, and the inequality is going to be maintained. And obviously, we know that from school level. But also, what would this mean? What would this mean? That would mean a squared is bigger than 0, establishing the relation given. If a is negative, then if a is negative, then we can multiply both sides by negative. Yeah? We can multiply both sides by negative. If multiply both sides by negative, then inequality is going to change direction, be greater than. Because if a is negative and you multiply by negative both sides, then you're going to have what? A greater than. So the inequality changes direction. And with that mentioned, we're able to then see we can multiply both sides by the positive number. Minus a is positive. It's bigger than 0. So we can just multiply both sides by that one. Bigger than 0. Where a squared is bigger than 0. Now, what is all this here? What exactly is all this? Now it is clear that the number 1 is equal to the number 1 times 1. 1 times 1 is indeed 1 squared. And so, if we agree that wherever there is a, we can choose a to be 1, so that we substitute 1 in the place of a, and therefore it would mean that 1 squared is 1, so that 1 is bigger than 0. Take a look. Take a look. And this is the proof to the fact that 1 is bigger than 0, given that we have a real number that is not 0, whose square is strictly positive. And then we move on to the next question. Okay, so the next one would be, if you let a and b be real numbers, let a and b be real numbers. If a is less than or equal to b plus epsilon, for every epsilon positive, then A is less or equal to 0. Then A is less or equal to 0. Let us prove this here. Let's look at the proof. We discussed the proof. We discussed the method of proof that we need to learn for exam purposes called the proof by contradiction. So we prove the result by contradiction. We prove the result by contradiction. How do we prove this by contradiction? To prove this by contradiction, so suppose that by way of contradiction, that A is less or equal to, okay. Suppose by way of contradiction that the conclusion is false. To prove this by contradiction, you suppose that the conclusion is false, and then deduce that also the hypothesis is going to be false, so that by means of the contradiction, we're able to achieve the result. Okay, the couple of ways we shall use to reason this, but let's just stick to the fact that first we assume that the conclusion is false, and we will work our way backwards to the premise. And to do this, we then say, okay, if we just assume that A is not less or equal to B, then B is smaller than A. If A is not less than B, A is not less, B must be the one that is less. But it's not only that A is not less, but A is not less and is not equal to B, which implies that okay. So whenever we then say that A is not less or equal to B, it means therefore that A is not less or equal to B, so B is the one that is less than A. And which implies that we can then be able to transpose the B having A minus B, in which case we shall have A minus B is bigger than 0. Indeed, this is the case from this by transposing and moving the B to the right-hand side of the inequality, like so. And we achieve that. Okay, these are very elementary proofs that we need to just to build our confidence with. So that we have 1/2 of the A minus B is greater than 0. We'll multiply both sides by 1/2. Now put epsilon. So now we multiplied both sides by 1/2, but 1/2 is a positive number, so the inequality does not change direction anyway. Now put epsilon to make this epsilon so that epsilon is 1/2 of A minus B. So we call this entity on the left of the inequality epsilon. In the statement of the theorem, write to obtain A is less or equal to A minus B is, okay. Now we put in the statement of the theorem. The statement of the theorem is that A is less or equal to B plus epsilon. So in the place of epsilon, therefore, we actually would put the a minus b over 2. And then we are able to do algebraic manipulations. This is equal to, what is this? Which is a plus b divided by 2. And this is less than. This is exactly less than. Because we already know that A is bigger than B. A is bigger than B. So in other words, in the place of B, we can put A because A is bigger. So this is going to be true because A is bigger than B. And this is equal to A. And this is very interesting. We get the absurdity. That says A is less than A. Okay, this means A is smaller than A. But this we know is false. The number cannot be less than itself. So which is a contradiction? Which is a contradiction? Which is a contradiction? Hence, our assumption that A is not less equal to B leads to a contradiction. Hence, if A is less equal to B plus epsilon for every epsilon positive, then we can be rest assured that A is less equal to B. Okay, yeah, the question is, what is the point of these results? Results we need to build our confidence with as we move to the most important section on, so this is just the preliminaries before we move to metric spaces. Okay. Now, there are certain things we need to remember and to just make sure we understand. The notion of an upper bound and the notion of a lower bound, the concept of a supremum and that of an infimum remain pivotal in understanding this module. Let S be a non-empty subset of R. It's a non-empty subset of the real numbers. We say S is bounded above in case there exists B in R, such that X is less than or equal to B for all X in S. Let S be a non-empty subset of R. So this is, S is not empty, but it's a subset of real numbers. So it is some subset of R that contains some real numbers, but surely it is not empty. It is not empty. We say S is bounded above if there exists a B in the real numbers, such that X is less or equal to B for all the X's in S. When is this set S bounded above? It's when we can take everything from S for all X's that are in S. For all X's that are in S. These X's are smaller than a B, and this B here is from the set of real numbers, the biggest set. Because of this, then we then say that S is bounded above, yet the upper bound of S does not belong to S even. It's essentially a member of the biggest set R. It's not a member of S, yet an element that is not a member of S is an upper bound of S. So the upper bound can always come from The upper bound can always come from the bigger set. Okay, you have the set of real numbers and a subset of it. We recognize that we're taking the B from R, yet the B is not in S, but the B is such that it is bigger than everything in S. By dint of these, then obviously we then say that B itself qualifies to be an upper bound of the set S. So upper bounds do not necessarily belong to the set that we are dealing with. Bounded below in the case, for example, when is the set bounded below? Bounded below is the same way. So in the same way, we take a C that is from R such that this C is smaller than the X. It's smaller than the X. Because of this C is smaller than the X. These X's, for all these X's in S, these X's are all bigger than C. You take all the X's from X, from the set S, but all of them, but with no exception, all the X's are bigger than what? Are bigger than C. C is difficult because C is way too small. It's smaller than everything in S, and therefore C qualifies to be called the lower bound of S, and therefore the set S, if such a C exists, is said to be bounded below. Okay, continue. There is a set that is bounded. Just bounded, not bounded above or bounded below, but just bounded. We say that S is bounded if S is bounded above and below. Okay, a set that is bounded above and below is said to be just bounded. So when you say a set is bounded, is bounded both above and also is bounded below. Okay, that is something that remains very, very important. So we continue to analyze these. We continue to analyze these as follows. Okay, let's continue, please. Thus, a non-empty subset S of R. Thus, a non-empty subset S of R is bounded above, respectively below, if there's a real number which is bigger than or equal to, respectively smaller than or equal to all elements of the set S. Such a real number is called an upper bound, respectively lower bound for the set S. Right, so we repeat the statement. Thus, a non-empty set S of R is bounded above, respectively below, or bounded below, if there is a real number which is bigger than or equal to. Real number bigger than or equal to, respectively smaller than or equal to. This real number C is smaller than or equal to all the elements of S. Such a real number is called an upper bound. We called it an upper bound in the first bullet point. We called it a lower bound in the next bullet point for a set S. Quite clearly, if B is an upper bound for S, then any real number bigger than B is also an upper bound for S. Okay? Quite clearly, if B is an upper bound for S, then clearly any real number bigger than B is also an upper bound for S. Okay, quite clearly, yes, because it's an upper bound. Right, so in other words, clearly, if B is an upper bound, B is an upper bound, then any real number bigger than B, right, is also an upper bound for S. Because you can find another one bigger than B, then it's an upper bound, yeah? Likewise, any smaller number any number smaller than a lower bound is itself a lower bound. In the same way, is itself a lower bound. Among upper, respectively lower bounds, we are interested in the smallest one. This is the infimum and the supremum. We're interested in the smallest one, respectively the largest. It is given a special name mentioned in the following definition. Let S be a non-empty subset of R, which is bounded above. Let S be a non-empty subset of R, which is bounded above. A real number alpha is called the supremum of S, denoted alpha equal to supremum of S. Okay, so first we begin with S. We let S be a non-empty subset of R, which is bounded above. So S is a set that is bounded above, but is a subset of R that is bounded above. Being bounded above, it actually therefore means that there's something that is bigger. There's a B there, but this B is an element of R, such that for all the X's in S, this B is bigger. So a real number alpha is called the supremum of alpha, of S, excuse me, denoted by the supremum of S is alpha. When is it the supremum? If alpha is an upper bound for S. So in the same way, you take everything in S, so you take the alpha, is an upper bound for S such that for all the X's in S, and then you have that this particular alpha itself is a real number, yeah? For any upper bound B of S, for any, so there can be other upper bounds. So these other upper bounds that exist, okay, if you have a supremum, any upper bound that you can find will be an upper bound that is actually bigger. Okay, and we come to these because there are many of these upper bounds, but there's this one we call the supremum. Okay, now, it's like there are many upper bounds, but we're interested in a specific one. Thus, the supremum of a set is an upper bound which is smaller. It's an upper bound, like in this case, alpha, which is smaller than any other upper bound. Okay, there are a couple of upper bounds. In this case, these numbers are ordered like this. So there's a number you can pick because this suprema, or a supremum is a number. So you can find a number that is bigger. It is also an upper bound. But that the supremum of a set is an upper bound which is smaller than any other upper bound. Smaller than any other upper bound. It is for that reason that if alpha is the supremum, is equal to the supremum of S, you choose alpha to be the supremum of S.
Hello?
Okay. Yes, please. Okay, we continue. It is for that reason that if alpha is equal to the supremum of S, we say alpha is the least upper bound, abbreviated the LUB of S. So you have the least upper bound. And the least upper bound is actually the supremum of S. In this case, it would therefore be alpha. So the supremum is the least upper bound. On the other hand, we have the following definition. Okay, let us look at definition 02.5. We begin with S being a non-empty subset of R, which is bounded below. So there's a set that is bounded below, but it's non-empty. Non-empty. A real number beta, a real number beta, real number B, but it's beta, right, is called the infimum of S, denoted. The infimum of S is beta. So beta is the infimum of S. But what is this? Okay, beta is a lower bound for S. If beta is a lower bound for S, okay, let S be a non-empty subset of R, which is bounded below. S is bounded below. A real number beta is called the infimum of S, denoted by beta equals the infimum of S. So when do we have this infimum here? If beta is a lower bound for S, okay, we defined a lower bound before, and here we then said the lower bound is like this, such that for all the x's in S, C in the real numbers, which is the biggest set R, and then we can pick a C, and this is our set S. This particular x here is bigger or equal to C. Bigger or equal to C. So we continue. Okay, we continue. For any lower bound D of S, for any lower bound D of S, the lower bound D, okay, here obviously we're calling it beta. But now what about if you find D? So you can find D such that the D is smaller than beta, but beta is smaller than X. For any lower bound, the lower bound is going to be such that D is going to be smaller than the lower bound that is there. So the infimum of a set S is called the greatest lower bound, GLB. Greatest lower bound of S. Greatest lower bound of S. So in other words, when we have a lower bound, we're interested in the greatest lower bound. There's nothing in the definition that says the supremum or infimum of a set must be an element of the set. There it is. Caution. It may or may not belong to the set. So that's why, so it may be outside the set. The infimum or the supremum, maybe outside the set. So something you need to take note of. Then in fact, the supremum of S is the largest element of S. In this case, we say the supremum is the maximum element of S. So now we introduce the notion of the maximum element of S, and frequently write maximum S in place of supremum S. Similarly, if, this is very important, this is special cases, if the infimum is a member, if the infimum of S is an element of S, we say it is the minimum element of S, and we may write that the minimum of S, we may write the minimum of S instead of the supremum of S, and hence now we have the minimum of S and then versus the supremum of S. Caution! You should never write minimum of S or maximum of S if the infimum or supremum is not in S. Is not in S. If the minimum supremum is not in S. We continue. We continue. There's a theorem. Let's look at this particular theorem here. Let's look at this particular theorem, quite an interesting theorem. Right, now, this theorem has two parts, namely A and B. So alpha is the supremum of S if and only if it is the least upper bound. Least upper bound, right, for all x and s. And this is true if and only if alpha is greater or equal to x for all the x's in s. So every x is smaller, so that you have an upper bound that is sort of the least upper bound. And this becomes the supremum. For all a that are smaller than alpha, so you can get an a that is smaller than alpha, there exists an s in the set S such that the a is smaller than alpha, but you can put another number between them. You can put another number between a and alpha, and this number you can put is an s. You can sandwich a number between the a and the alpha. Okay, this is just a theorem, but nothing very special about it. Okay, but obviously it's helping us to build towards very important results. Okay, let's speak about the infimum. So if beta is the infimum of S, this is true if and only if beta is less or equal to X for all X in S. And for all B bigger than beta, there exists a W element of S such that you can put this W, because you have that beta is smaller than W, is rather beta is smaller than B, excuse. Okay, we start with beta is smaller than B from here. Beta is smaller than B. Then we can be able to sandwich a W between these. These are numbers. You can put these. I mean, you can have 3 is smaller than 5, yeah? 3 is smaller than 5, and then you can agree that, okay, you can put a number. 3 is smaller than 5. You can put a number, 3 less or equal to 3 is less or equal to 2, but 2 is also smaller than 5. Perhaps not. Okay, put the number 4. Put the number 4. Indeed, the number 4 is bigger than 3, yet the number 4 is smaller than 5. So you can have that kind of a case. But in other words, you can be able to, note these particular relations. Okay, this is a theorem, but let us try to understand it briefly before we proceed. If beta, you take beta to be the infimum. What is the infimum? Is the greatest lower bound of the set S. So beta becomes the greatest lower bound of the set S, called the infimum, if and only if beta is smaller than every single bit of thing. It is a lower bound, it is smaller and hence a lower bound, but it is the greatest one because we choose it such that it is smaller than everything in S, but yet the greatest. And for all B bigger than beta, we can always, in other words, we can get something that is bigger than a B that is bigger than beta. In the same way here that we got an A that was less, because this is the least upper bound. But here we're dealing with the greatest lower bound. So it's finding a number that is bigger. B is bigger than beta. Then we can find there exists some W in S, such that this W you can sandwich. You can form a sandwich and put it between the B and the beta and the B. Okay, so this is like sandwiching. Okay, it's just some theorem that has been developed, but nothing very peculiar about it. I want us to discuss some of these. These are all preliminaries and basics you need to know. But the least upper bound property. What is the least upper bound property and what does it say? Every non-empty subset of R that is bounded above has a supremum, or has the supremum. Okay, so it's language. Every non-empty subset of R that is bounded above. If you take a set that is bounded above, because it is bounded above, then you can find a supremum, because a supremum is what? Is the least upper bound. Least upper bound. Least upper bound. Every set that's bounded above has the smallest upper bound. Because it's bounded above, it has the smallest upper bound. But that smallest upper bound is also called the least upper bound, and hence there is a supremum that we have. What the LUB property says is that if S is a subset of the real numbers, is non-empty and bounded above, S is non-empty and bounded above, then there is a real number alpha, so that this alpha is the supremum of S. So that alpha is the supremum of S. In order to fully appreciate the power of this axiom, let us consider a situation where we pretend the only numbers we know are rational numbers. Yeah, we just assume we're dealing with rational numbers only, and we do not use other numbers. Then the concepts of bounded above, supremum, and supremum are definable in Q exactly as we did in R. Okay, yeah. So in other words, then the concept of bounded above, we defined them in R. R was our universal set, but now these concepts of bounded above and supremum are definable in Q exactly. So we can decide, okay, we're going to be dealing with rational numbers and not just real numbers. Okay, just a setup. Now, Q does not have the LUB property. Indeed, okay, let us check that Q does not have the least upper bound property. Doesn't have the least upper bound property, the supremum property. Indeed, if we let S be a set that contains all Q, these Q are rational numbers. So Q itself is an element of, X is an element of Q, like this, such that X squared is less than 2. Then S is a non-empty subset of Q. Very interesting. It is non-empty. So it contains some rational numbers, yeah, which is bounded above. However, there is no rational number R such that R is the supremum of S. Okay, let us reason together with the author. We're just looking at this set and we're interested in finding its supremum before we move on. Okay, now the question is, what then is the supremum of this set? However, working in R, we have got the supremum. Okay, because if ever X squared is less than 2, we can have the quadratic like this. Minus the square root of 2, the square root of 2. Okay, and when we're interested in finding what? The least LUB property, the least upper bound. The least upper bound. But obviously, if we're in R, then we're able to see, oh, okay, these are the real numbers. And now we're actually able to take that from this particular relation here, if this X squared is less than 2, you can then say X squared is less than 2, which means what? X squared less than 2, you can write it as X squared minus 2 less than 0. Which is this? It would therefore mean that here we're looking at where this inequality is negative. So that is going to be this part here of the inequality. And obviously the solution to this inequality would have to be minus square root of 2 is less than X less than. But in this case, therefore, the square root of 2 it's a real number. It's not a rational number. Okay, and hence now we can then say the upper bound, the least upper bound, yeah, is the least, because you can see this graph goes up like this, and there are other bounds that are there. Like you can put a 2, you can put 100. 100 is bigger than this, but the least upper bound is going to be square root of 2, so that we can indeed say the supremum of S is the square root of 2, which is the least upper bound, yeah. But now this least upper bound is in the set R, it is not in Q. Okay, let's look at this remark here. The LUB property is also known as the completeness axiom for R. LUB property is also known as the completeness axiom for R. Let us discuss the completeness axiom for R. Okay, these are like basics. But first, the denseness of Q in the real numbers, the denseness of the rational numbers in the real numbers. In this section, our main goal is to prove a very important result, which states that between any two real numbers, there is a rational number. Between any two real numbers, there is a rational number. Between any two real numbers, you can find a rational number. The set N is not bounded above. Let's look at this theorem. The set of natural numbers as we defined it is not bounded above. Let us analyze this and look at the significance of this. The set of real numbers is not bounded above. Let us look at the proof. Okay, to prove this one, we begin as follows. We look at the proof. To prove this, you assume N. Want to show that it is not bounded above. The set of natural numbers is not bounded above. How do we prove that? You assume N is bounded above. You assume the opposite, because they're saying prove it is not bounded above. For a proof by contradiction, we assume it is not the case. We assume it is bounded above. Then, by the completeness axiom, by the completeness axiom, the supremum of this exists. Okay, if we assume the contrary, that it is bounded above, then it has an upper bound. If it has an upper bound by the completeness axiom, and we have said the LUB property, this LUB property is also known as the completeness axiom. So if then we say there's the least upper bound, then it means that we can use the completeness axiom, yeah? So then by the completeness axiom, the supremum of N exists. How? Because we assume that N is bounded above, and therefore it has a supremum. It has the least upper bound. It is an LUB. What we do then, we put these, call this supremum of the natural numbers, call it alpha. Yeah, let's give it the name alpha. Since we can subtract 1, this is by construction, algebraic construction. So we can subtract 1 from this supremum. If we subtract 1 from the supremum, alpha minus 1 is smaller than alpha. It is true. Because these things are natural numbers. We're taking the natural number alpha and then we subtract 1. Maybe if it is 3, you subtract 1, you get 2. 2 is smaller than 3. So we subtract 1 is smaller than that. Alpha minus 1 is not. Is not an upper bound. It's not an upper bound for N. Alpha is not an upper bound for N. Okay, we continue, we shall elaborate on that. So there exists a K in the natural numbers. Yeah, such that alpha minus 1 is actually smaller than k. Smaller than k. This implies that okay. Since alpha minus 1 is less than alpha, indeed, when we subtract 1 from a number, it is smaller than the previous number. And then we note that alpha minus 1 is not an upper bound for n. Okay. So there exists a k from the natural numbers such that the alpha minus 1 is actually smaller than k. Okay, we shall make sure we understand this. But this implies that alpha is smaller than, now you can move the 1 to the other side. Alpha is smaller than k plus 1. So just transpose the 1 to the other side. Right. But k is less than n. Means that k plus 1 is an element of n. But k is an element of n. This implies that k plus 1 is also an element of n. Okay, but obviously by choice, we chose that k is an n, and therefore if you add 1 to a natural number, indeed the k plus 1 is also an element of n because just added 1. And this means so the k plus 1 is less or equal to alpha. Okay, we're back. So k plus 1 is less equal to alpha. Okay, we shall have just a synopsis of this. This is true since alpha is an upper bound. It's an upper bound for n. Alpha is an upper bound. So we said that alpha is an upper bound because of the LUB least upper bound property. Then we have that the k plus 1 is an element of n. K plus 1 itself must be less or equal to alpha. Why? Since alpha is an upper bound of n. If it is an upper bound of n, therefore, if you pick anything, k plus 1, we're picking it from n, then it must be bounded above by this alpha because it is a natural number. Every natural number will have to be bounded by the alpha because it is an upper bound. It is above anything. Since alpha is an upper bound for n, okay, thus, alpha is less than k plus 1, less or equal to alpha. Since alpha is an upper bound for n, then we can do this because alpha is above anything that is a natural number. Thus, it means, therefore, we can be able to sandwich, like we formed sandwiches using the former result. So you can put the k plus 1 between alpha and alpha, but just that this k plus 1 is smaller, it's rather bigger than alpha, but less or equal to alpha, which is absurd, which is a contradiction. which is absurd. And this concludes the proof. Okay, let us just look at this particular theorem. Okay, it's not everything that should concern you, but in the learning of this module are the theorem statements. You might not understand something in a proof, but what you need to remember always is the statement of the theorem. What is the statement of the theorem 3.1? It is the fact that the set n of natural numbers is not bounded above. The set of natural numbers is not bounded above. So to prove this now, we attempted to prove it by contradiction. And the way to prove things by contradiction is to assume the contrary. So assume n is bounded above. Because it's saying we need to prove it's not bounded above. So we assume it is bounded above. Then by the completeness axiom, which is the LUB property, then it means that if it is bounded above, then it has an upper bound. With an upper bound, then it means, therefore, that you can always be able to get something that, a bound that is above everything. So, now, which means a supremum exists. The supremum exists. Put alpha to be the supremum. Put alpha to be the supremum of the set of natural numbers. Since now we perform some algebraic manipulation, and then say alpha is the supremum, we can subtract 1 from it. Yeah, we're dealing with natural numbers, and 1 is a natural number, so you can do the subtraction here. But alpha minus 1 is smaller than alpha. It is indeed smaller than alpha. Okay, yeah. Alpha minus 1 is smaller than alpha. Alpha minus 1 is not an upper bound for n. Why is alpha minus 1 not an upper bound for n? Because already we are taking something smaller. So an upper bound would have to be bigger. But now we subtract it, yeah? It's not an upper bound for n. So there exists a k in the natural numbers such that alpha minus 1 is actually smaller than this k. So this k becomes an upper bound for, this k becomes an upper bound for the alpha minus 1. Yeah? But now, if the alpha minus 1 is it's in the natural numbers. So, and we subtract 1 from it. So there exists a k in the natural numbers such that alpha minus 1 is less than k. So you can find a k that is bigger than the alpha minus 1. But this k is in the natural numbers. This implies that we can perform algebraic manipulations and then move the 1 to the other side so that alpha is less than k plus 1. But k is in the naturals. And this means k plus 1 is an element of n. K plus 1 is an element of n. Okay, so k plus 1 is less or equal to alpha. Because alpha is the upper bound. So it means that it's above the kinds of things you can take, the kinds of elements of n. Since alpha is an upper bound for n, this is going to be true, yeah? It's an upper bound. Alpha is an upper bound, so it's a supremum. Thus, which means that we can be able to form these here. What do we have here? We have that alpha is less than k plus 1. But k plus 1 is less equal to alpha. So alpha is less than k plus 1. Okay, so alpha is less than k plus 1, but simultaneously k plus 1 is less than alpha, and therefore it means that alpha is less than k plus 1, this is less equal to alpha, which is absurd, because alpha is less than itself. A contradiction, and hence it is appropriate to assume that n is not bounded above. Is not bounded above. Okay, we move on. Given a real number r, there exists an integer k such that this k can be found between the real number -1 and the real number r. Let us prove this one here. Let us prove this result here. To prove this, so we look at the proof. Right, to prove this, you need to find an integer. We need to find an integer m such that m is less than r. To prove this, you need to find an integer m such that m is smaller than r, because we're starting with the real number r. So now we're saying we need to find an integer m such that m is smaller than r. And a natural number right, and a natural number n such that in a natural number n such that n is bigger than r. Thus, m is smaller than r, but r is smaller than n. Notice that since m is less than r, okay, r is less than n. Yeah, r is less than n. Notice that since m is less than r, yeah, according to the hypothesis, m is less than r and r is smaller than n. Yeah. In the set, m n. Okay, let's check this out. There. Okay, we're going to actually discuss the integrities of this, but we're saying there is the largest. There is the largest k such that k is smaller than r. So k plus 1, we shall discuss this, but it's bigger or equal to r, and therefore we can subtract 1 from r, get less or equal to k, and this is less than r. Let us look at the integrities of these. We need to find, given a real number r, we need to show that there exists an integer k such that this k can be put between r minus 1 and r, such that r minus 1 is less or equal to k, yet k is smaller than r strictly. So you need to find an integer m such that m is smaller than r. You need to find an integer m such that m is smaller than r. Okay. And a natural number n such that this natural number is bigger than r. So we're dealing with two integers. One is smaller than r, the other one bigger than r. We are consistent with this. Smaller than r, bigger than something. K is smaller than r, yet is bigger than r minus 1. Thus, m smaller than r, smaller than n. So in other words, we want to find two numbers that are such that n is sort of an upper bound and m is sort of a lower bound here. M becomes a lower bound and n becomes an upper bound, and we just want to form this sandwich. Notice that since m is smaller than r by hypothesis, and also r is smaller than n by hypothesis, in the set m plus 1 to n, there is the largest k. We can get the largest k such that k is smaller than r. We can get the largest k such that k is smaller than r. Thus, okay, let's just look at these carefully. So in other words, given the number r, we want to find m and n such that can do this. Yeah, these are numbers we can try to find, but these are real numbers because r is a real number, so you can find some real numbers m and n that can put r between them. And notice that since we agree that indeed m is smaller than r and r is less than n, in the set m plus 1 to n. Okay, look, by dint of this, we're ordering these numbers, but m is the smallest of the numbers, and then n is the largest of the numbers. Yet now, because m is the smallest, you take the smallest one, we add some numbers until you get to n. We start with m plus 1, m plus 2, m plus 3, until n. And if we then say, notice that since m is smaller than r and also r is smaller than n, in the set where we have the m numbers, m plus 1, until, start from the smallest one, you add until you get n, there is the largest k, such that we can get the largest k from this set. And since we can be able to get the largest k from this set, what then are we able to do? We can be able to get the largest k from this set such that this largest k is smaller than r. Then there is the largest k such that this k is smaller than r. It's smaller than r. And so, because of this, so the k plus 1 is bigger than or equal to r. So there is a largest k Okay, there's the largest k. I want us to pause and reason this out. Okay, there's the largest k such that this k is smaller than r. Remember that these are the m plus 1, and n. And these are sort of the values that you have m and up to n, m plus 1 up to n. So now we want to find a k. A k, we understand that sort of must come from this set, meaning it can be an m plus 1 and m plus 2. So there is a k such that this k is smaller than r. Okay, if this k is going to come from this set, now the k can be what? The k can be m plus 1. So that the m plus 1 is also smaller than r. If the k is smaller than r, then we can find a k plus 1 that is bigger than r. We can find a k plus 1 that is bigger or equal to r. Okay, so in other words, now we can find a k that is smaller than r, and the k is going to come potentially from this set. So we're then saying if we add 1 to the k, so that we have k plus 1, this k plus 1 is actually essentially will be such that it is bigger than r or equal to r. And therefore, it means now you can perform algebraic manipulations. If k plus 1 is bigger than r, it means that k is bigger equal to r minus 1. K is therefore bigger equal to r minus 1, yet k is less than r. And therefore, we can be able to find this inequality here. We can be able to find this inequality there. I want us to reason these, but reason these carefully. At this point that we're then saying, we have these particular numbers and they're ordered like m is smaller than n, and then we construct this set, m plus 1, m plus 2, until we get to the largest number. Then after that, from the m to n inequality, then we form this set, we construct it. Then we're then saying there is the largest k. Remember, this k is the largest, such that this k performs this task. What is the task? This k is like, it's smaller than r, so it's one of the m's. It's one of the m's, but m is smaller than r, so we're saying there is the largest k, such that this k, but the largest one, such that it is smaller than r. Remember, m is smaller than r, but we can get some m plus something, which we call k, the m plus 1, m plus 2, we call k, so that it is smaller than r, yet it is the biggest k. So with this in mind, then we can be able to then say, so k plus 1 is bigger or equal to r. So k plus 1 is bigger or equal to r. Okay, so that we then say k plus 1 is bigger or equal to r. Okay, because the k is the largest one. Yeah, the k is the largest one that is smaller than r, but the largest that is smaller than r. So in other words, you can get a 2 that is smaller than 3 if 2 is the largest one. Of course, these are real numbers. Then we can add, if you add the 2 plus 1, 2 plus 1 is indeed greater or equal to the 3. So indeed, this is algebraically correct. If 2 is the largest one, if you add 1 to it, the inequality reverses. And therefore, now we can perform algebra and then say R minus 1 is less or equal to K. R minus 1 is less or equal to K. Yet K is smaller than R. And therefore, given a real number R, try to understand this. Given a real number R, there exists an integer K, and this K can be put between the real number R minus 1 and the real number R. Okay, just try to digest that and process that. Okay, we move on. Okay, there's another corollary 03.3. Let A be a real number and epsilon positive, then there exists n in the naturals such that n epsilon is bigger than A. Informally, no matter how large A is, how small epsilon is, as long as epsilon is positive, we can add epsilons, enough epsilons to obtain a result larger than A. Okay, let us prove this one. Let us look at the proof of this. Now, to prove this, we begin as follows. Let us look at the proof. If not the case, then you can have n that is less or equal to the number A over epsilon for every. For every n in the naturals. Contrary to the fact that n is not bounded. Is not bounded above. If not, okay, let's start by looking at this. Let A be a real number. A is a real number, and epsilon be positive. Then there exists a natural number n such that if you multiply n with epsilon, it is bigger than A. Informally, no matter how large A is and how small epsilon is, as long as epsilon is positive, we can add enough epsilons to obtain a result larger than A. Okay, so we take a real number. This is the interpretation, and it's a very interesting interpretation. That in this case, then you take A being a real number, and then you take epsilon. And now you want to add as many epsilons, which are very small, as possible, such that the summation doesn't matter how many they are, but you can get to a point where the sum is immediately bigger than a given real number A. Yeah, even if this epsilons are very small, maybe epsilon can be like 1/2. If epsilon is 1/2, how many 1/2s you need to add if the number is 4? So you can add so many of these, such that in the end, then you find that the sum of these epsilons is bigger than A. Obviously, now informally, no matter how large A is and how small epsilon is, as long as epsilon is positive, we can add enough epsilons to obtain this result. Okay, let's look at how we prove this. If not, we assume it's not the case. So we reverse this inequality. because it is n epsilon greater than a. So we must make it less than or equal to, yeah? If not. So in other words, now you divide by epsilon so that n is less or equal to a over epsilon. We assume the contrary for every n in the natural numbers, contrary to the fact that n is not bounded above, yeah? So it is contrary to the fact that n is not bounded above. Because it's contrary to the fact that n is not, because this is creating n is a natural number, and then now if n is a natural number, it is saying that the set of natural numbers is bounded above. Yet we just proved that n is not bounded above. So this is contrary, because this is saying n is bounded above a natural number. Given a natural number n, you can find an upper bound. And obviously, we know that the set of natural numbers is not bounded above. This is contrary to that. And therefore, reversing this, assuming the contrary, leads to a contradiction. And hence, indeed, it is true that given any real number a and epsilons that are positive yet very small, we can add enough of them. But enough of them so that the sum is bigger than some real number a in the set of real numbers. So something to ponder on, but a very little result there. We move on to the next question. Right, next we look at the theorem. Theorem 03.4. Theorem 03.4. Okay, let x and y be real numbers and with x less than y. Then there is a rational number r that you can put. Between any two real numbers, you can always put a rational number. Then there's a rational number. And you can argue. Given two real numbers, you can put a rational number between them. Can we not put an irrational number? Yes. Okay. But now we'll first begin by proving we can put a rational number. Let's look at the proof. Let's look at the proof of this. So to prove this, you choose. So given any two real numbers, 2 and 3, you can find a rational number that is between them. Yeah? You can find 2.5. 2.5, for example. 2.5 is the number that is between these. And yet it is a rational number. And you can argue, okay, we are sure of rational numbers, but given two real numbers, 2 and 3, can you find an irrational number? Yes, you can. Okay. But now we prove the rational case. So choose a natural number such that one over n is less than y minus x. Then x is less than y minus 1 over n. Okay, choose n element of the natural numbers such that 1 over n is less than y minus x. Okay, this one is a choice. It's a construction. It's a construction, but let us look at whether it's going to help us or not. It's a construction, very, very clever construction, but let's check if it's going to help us. So then with this in mind, you can manipulate and move the x to the one side and move the 1 over n to the other side. And this is what we're able to obtain. By corollary. Right, by corollary. By corollary. Okay, don't need to quite worry about the corollary, but we went through it. Yes, which is the one just proved now. By corollary 03.2, we can find an integer k. We can find an integer k such that ny minus 1 is less or equal to k less than ny, that is y minus 1 over n is less or equal to k over n. We shall look at the merits of these. By corollary 03.2, remember we said we can find a k. And this k is going to lie between this number minus 1 and then the same number. The r minus 1 and then the r, but you put the k between these. And that is, you can divide through by the n because the natural number and the natural numbers are positive. So you can divide through by n, getting y minus 1 over n, and then k, getting k over n, and then getting n. Combining these results, we obtain x less than y minus 1 over n is less or equal to k over n less than y. Which implies that x is less than k over n less than y. Okay, let us analyze these, combining. Okay, let us pause to reason this out together. Okay, what is this theorem saying? Between any two real numbers, if let x and y be real numbers with one real number less than the other, so x is less than y, then there is a rational number r that we can get that lies between the two numbers x and y. So you can sort of form these sandwiches in the set of real numbers. Between two real numbers, you can find a rational number that is between them. Yeah. So to do that, let's write a proof. How would you prove that, and how would you construct the proof? So this is a very, very tricky proof. But we begin with the construction, a very clever one. We then saying choose a natural number. Why natural numbers? Because it is relevant, and now we want to form rational numbers. We want to deal with rational numbers, so we can deal with n being a natural number, because what to form. So we can deal with natural numbers, which are easier. Oh, but obviously, I'm sure that you can start. Okay, to form rational numbers. How do you form rational numbers? You form them with integers, so you can form x over y. So you can imagine that, okay, why don't we just begin with integers? But your integers are a little bit problematic because you can have a case where 0 is one of the integers. 0 is an integer. So yeah, we, for purpose of this proof, begin with n, which is the natural number, such that 1 over n is less than y minus x. Okay, 1 over n is less than y minus x. So we're beginning with this construction here. Then, what does this mean? Then we perform algebraic manipulations, yeah? And then we say we can move the x to the other side, to the left, and then the 1 over n to the right. And this is what we get. By corollary 03.2, we can find an integer k such that this integer k, we can sandwich it. Like we use the corollary 032. So now, the kinds of numbers we can have here now, if you multiply through by the n, you're going to have an ny minus 1. So now you have the ny minus 1 is less or equal to k, is less or equal to ny. In the same way that before we just said r minus 1 is less than k, less than r in that corollary 03.2, we just did now. But now our R, it's like the ny, because this construction is very clever, because if you multiply it through by the n, you have ny minus 1, which is ny minus 1 is the, so from this you get nx is less than ny minus 1, yeah? So if you have the ny minus 1, then you can imagine, okay, we can be able to form something, the ny minus 1, so you can look at ny minus 1, ny, and then put a k between them, yeah? Because we said that this is true for real numbers. And that is to say, we can divide it through, because the k came from the previous corollary. That's the method we used, or the symbols we used. So now we can divide through by the n, getting y minus 1 over n, and k over n is less than n. We divide it through by n because the natural number is not 0, etc. Combining these results, you obtain that x less than y, or x less than this, less than x less than y minus 1 over n, less than or equal to k over n, less than y. Okay, let us look at combining these results and the implications of these. So, but I mean, at this point, we agree that if you divide right through, but first from this point, x is less than y minus 1 over n. So indeed, x is less than y minus, this is how we started. Yet, at this point, if you divide through by n, you are able to get y minus y over n is less than or equal to k over n. This is less than y. Which implies that x is less than k over n less than y. And this is a rational number. So between the x and the y, we have put k over n, which is a rational number. What a clever construction. And this means that between any two real numbers, x and y, you can form a sandwich and put a rational number that lies between any two real numbers. And this is the proof. Okay, some of these proofs, these are very important results in reanalysis. So it's something to think about and make sure you ponder on. But let's look at the next little problem. In corollary 03.5, let B be a real number and S be the set of, S is the set that contains x's that are elements of the rational numbers such that x is less than b. Then the supremum of S equals b. Then the supremum of S equals b. Let us write the proof. Let's look at the proof of this. Clearly, S is bounded. Is bounded. Let's first start there. Is bounded above because of the LUB property, supremum. The supremum suggests that the least upper bound property, also called the completeness axiom, holds true. So in other words, clearly S is bounded above. How do we know this? We know this because there is a supremum there, yeah? Okay, but obviously we need to say then the supremum is B. We just need to confirm it is B. But clearly S is bounded above. And so has a supremum. Has a supremum. Say C. Then C is less or equal to B. Since B. Okay, we shall look at the nitty-gritties of these. But since B is an upper bound, since B is an upper bound for S, is an upper bound for S. If we assume that, right, if we assume that C is less than B, then there's a rational number. There's a rational number. There's a rational number R such that C is less than or less than B. Okay, we shall look at the integrities once again and make sure we understand this. But we are saying that so R is a number. R is a number. Is rather a member. Is rather a member. We're going back. Is rather a member is rather a member of S. That is strictly larger than the supremum of S. That is not possible. Okay, we shall get to the nitty-gritties of this and sensibility of this. So C itself is not smaller. It's not less. It's not less than B. Hence C equals B. Hence C equals B. Okay, let us look at this here. Okay, now in view of this corollary, obviously this concluded proof, but I want us to just get a sense of what is happening with this proof, but also it will train us to be in a position to understand the supremum and the infimum very well. But now we then are saying, let B be a real number, and S be the set that contains X, which is an element of Q, such that X is smaller than B. B is a real number. So X, the set S contains some rational numbers, X, that are all smaller than B. In other words, B is sort of an upper bound of everything in S, and therefore, clearly, that's what we're saying here. And if this is true, so that B is an upper bound of everything in S, because B is bigger than all the X's, and B is a real number. So it's a sort of scenario we've been talking about here. So you're dealing with the set R, and then you're dealing with the set S, and then we can pick a B that is not necessarily in the set S, but this B is bigger than everything X. Then the supremum of S now equals B. Okay, this is very interesting. Then the supremum equals B, yet B is a real number, but S contains rational numbers, so the supremum of a set of rational numbers is a real number. And this real number is not even in S, and therefore this further through this corollary confirms that indeed the supremum need not be in the set S. Somebody says we need to find the supremum of S. We don't have to look in S only. We need to look in the bigger set of real numbers to see if we can find the supremum there. Okay, now clearly S is bounded above. How do we know? It is bounded above because S contains all X's in Q such that all the X's are smaller than B. B is sort of an upper bound of all the X's. So indeed, clearly S is bounded above, and so has a supremum. And so has a supremum. Say, let's call that supremum C. Then this C, because it's the supremum, and a supremum is the least upper bound. Least upper bound. So in other words, the supremum is the least upper bound. Okay. So if we agree that this supremum is the least upper bound, then C is what? Then C is such that it is less or equal to B, since B is an upper bound for S. Yeah? Because since B is an upper bound for S, then you can get something smaller. Yeah? You can get something smaller because this B is bigger than the thing, so we can get something smaller than B. Yeah? If we assume that C is smaller than B, then there is a rational number R. We assume that C is less than B, so you can find a rational number R that sits between the two. So R is a member of S that is strictly larger than the supremum of S. Larger than the supremum of S. That is not possible. That is not possible. So, okay, let us look at the possibility of this. Okay, we want to order some numbers, yeah? We're calling C the supremum because we can see that clearly S is bounded above because it has a B and the B is bigger than all things, so it has some upper bound. And let's say C. And if C is the case, now clearly it's bounded above and so it has a supremum, say C. We say C the supremum of S. Then C obviously itself is such that, right, so we take then C to be less or equal to B. So C is less or equal to B. Why? Because since B is an upper bound for S, so it's an upper bound, so we take the things that are smaller. If we assume that C is less than B, if we assume that C is less than B, then there is a rational number, yeah? C is less than B. Then we have the number C is less than B. Say these are numbers. These are numbers, real numbers. Then there is a rational number R that we can put between. Okay, we discussed that as part of the previous theorem. Given two real numbers, then you can sandwich. You can form this sandwich and put a rational number between them. So R is a member of S. R is a member of S. R is a member of S. That is strictly larger than the supremum of S. R is a member of S, and R is strictly larger than C, and C we said is the supremum. So it is strictly larger than the supremum. But the supremum is the least upper bound. Is the least upper bound by the completeness axiom. So R is a member of S that is strictly larger than the supremum of S. So R is strictly larger than C, where C is the supremum of S. This is not possible. It can't be possible. It can't be possible because we have already said that C is the supremum of S, and it is the least upper bound. The least upper bound. So it is not possible, therefore, to find that R is bigger. Because that would then make R bigger than S, meaning it is an upper bound also. So it's not possible. So it means, therefore, C is not less than B. So So S is not less than B. Why? Because now assuming that C is less than B leads to problems. And hence C is effectively equal to B. So that C equals B, that means that the supremum of S is equal to B, is not C or anything else. It is B itself. This means we have a situation where B is a real number and it is an upper bound. It is the upper bound of a set of rational numbers. So the supremum can always come from outside the set. It came from the real numbers now. So that is something that we have here. So we have this. We have this. So we continue. We continue. Okay. Now, I want us to explore this case here in line with this corollary 03.5. Now, let us go back. Let us go back to the case. Let us go back to the case S equals X in Q such that X squared is less than 2. Mentioned earlier. Mentioned earlier. Mentioned earlier. Note that X squared is less than 2. Okay, we saw that X squared less than 2 means that the square root of 2 is less than X less than 2. Okay, this one we learn at school. Minus the square root of 2, the square root of 2. And this X squared less than 2 is the same as X squared negative. X squared minus 2 negative. It means therefore we're interested in the part of this that is below the real line. And therefore X would therefore lie between minus 2 and 2 inclusive. So by the foregoing corollary, we have that this corollary, we have that because we're learning how to find the supremum just because it's an interesting thing to do for us to understand the course. We're able to see therefore that indeed, square root of 2 here. So we're able to see that indeed the supremum is the square root of 2. So we're able to see that the supremum here is indeed the square root of 2. And the supremum is the least upper bound using what we call the least upper bound property, or what we also call the completeness axiom. Right. So in other words, by dint of the least upper bound property, we're able to say, okay, right. we're able to say that the set, which is X and Q, because these kinds of exercises, they came in the assignments and so on. Okay, but obviously they can just change the inequality, but you see the pattern of reasoning is the same. So if X squared is less than 2, then we can solve for X and get these. And then from these, we just choose the least upper bound. You're following the least upper bound property, and the least upper bound is this one. Why is it the least? It is an upper bound when it's bigger, but there are other upper bounds like 100. 100 is bigger than this in terms of numbers, ordering of numbers, but also this graph would go to as far as 100 there. But now this graph is going to go as much as 100, in which case, therefore, this would be numbers of interest. But I must indicate that there are other numbers here. Square root of 2 is 1 point something, but what about if you pick minus 1 and 1? So you can pick the number 1 that is smaller than 1 is smaller than the square root of 2, because square root of 2 is like 2 point something, yeah? Yet, strictly speaking, we understand, therefore, that the square root of 2 would be the least upper bound. It is the least upper bound. In other words, there are other upper bounds that exist bigger than the square root of 2. Okay, try to digest these and get to think about it. We define next cardinality. Right, cardinality is very important, and most of the times it's assessed also in the exams and things. Our treatment of this topic will be rather superficial, the main purpose being to establish that any interval from A to B with A less than B has as many elements as R. Between any two real numbers, there is a rational number. Okay, we have already established that. But any interval from A to B with A less than B has as many elements as R. Okay, hey, this is very powerful. If you take an interval like this, it has as many elements as R. In other words, the cardinality of this is the same as the cardinality of R. The cardinality of an interval is the same as the cardinality of R with A less than B, A not equal to B in the real numbers. By a finite set, we mean an empty set. What is a finite set? By a finite set, we mean an empty set or a set that has n elements for some n in the naturals. Okay. Now, if S and T are finite sets with m and n elements respectively, then it is clear that there is a one-to-one function f from S to T mapping S onto T, if and only if m equals n. Generalizing to arbitrary sets, including those with infinitely many elements, it is natural to think of two sets as having the same number of elements, yeah? We can think of two sets as having the same number of elements. So cardinality is to do with the number of elements in a set, provided there is a one-to-one function between them. We caution that this may go against intuition in the sense that a proper subset of a set can have the same number of elements as the set. Right, so we witness the following example. Let's look at the following example. Let's look at example 04.1. Let S be the set of all even natural numbers. Okay, set of all even natural numbers. What are they? Okay, yeah, all even natural numbers. So we can think of S as, right, natural numbers 2, 4, 6, 8, and so on. Then S is a proper subset of N. It's a proper subset of N, so but it's not equal to N, so it's proper. And it's not, because this one is proper. It's a proper subset. And this one is improper. is improper subset. The function f from n to s given by f of n equals to n is 1-to-1 onto. Okay, if s is the set of all even natural numbers, like you said, 2, 4, 6, 8, and so on, then s is the proper subset of the natural numbers, right? The function f from n to s given by, okay, here's the function. The function that moves from n to s is fn equals 2n, is 1-to-1 and onto. Let's justify this. Clearly, then, in the case of infinite sets, to say two sets have the same, okay, this is very important. Infinite sets. To say two sets have the same number of elements might be problematic because the sets are infinite. Can they have the same number of elements? We therefore speak of sets having the same cardinal number or cardinality, where in case of finite sets, the cardinality of a set is simply the number of its elements. Okay, in the case of finite sets, the cardinality of a set is simply the number of its elements. We shall not define precisely what a cardinal number is. That is a matter normally discussed in a course on set theory. Okay. We therefore speak of sets having the same cardinal number or cardinality where in the case of finite sets, the cardinality of a set is simply the number of its elements. The cardinality of a set in the case of finite sets is simply the number of its elements. Right. But once again, clearly, then in the case of infinite sets, to say two sets have the same number of elements might be problematic because the set is infinite. Can we count and say, because it's like each of the sets is infinite? We therefore speak of the sets as having the same cardinal number of cardinality, where in the case of finite sets, the cardinality of a set is simply the number of its elements. Right, so infinite sets, same number of elements, problematic. Okay, yeah, because we learned that we will discuss this because we'll discuss the cardinalities of these infinite sets in detail in our next meeting. Okay, let us say this. Let's look at definition 04.1. Let S be a set. We start with the set S. A symbol called the cardinal number of S, denoted by card of S, which is the cardinal number of S, where S is a set. Or you can say this to mean the cardinal number of S is associated with S in such a way that the cardinal number of X is equal to the cardinal number of Y, if and only if there is a 1-to-1 onto function from X to Y. The cardinality of X okay, look, we are here. I want us to pause in the okay. Let S be a set. A symbol called the cardinal number of S, denoted by the cardinal number of S, or the modulus of S, which refers to the cardinal number of S, is associated with S in such a way that the cardinal number of X is equal to the cardinal number. So when are two elements having the same cardinal number, even only if there is a 1-to-1 onto function from X to Y. If S is a finite set with M elements, we set the cardinal number of S to be M. When are two sets having the same cardinal number. This is true if and only if there is a one-to-one function from x to y. Then you can say the cardinality of x is equal to the cardinality of y. In other words, the cardinal number of x is equal to the cardinal number of y if and only if there is a one-to-one function, one-to-one onto function from x to y. If S is a finite set with m elements, finite set with m elements, we set the cardinal number to be m because we can just count. We can just count the elements there and find that, oh, the elements are what? The elements are just only m, because m is a finite, S is a finite set. As special numbers, we mention the cardinality of n, which is normally denoted by aleph naught. Okay, the cardinality of the natural numbers is actually denoted by aleph naught. The symbol n like this is a Hebrew letter pronounced aleph, and the cardinality of r we denote by just aleph. So now we come to the following point. What is the cardinality of r? It is aleph. What is the cardinality of the set of natural numbers? Is aleph naught. Yet, obviously, you agree that both of these sets, the natural numbers and the real numbers, are both infinite sets. Next, we define what it means to say one cardinal number is smaller or smaller than or equal to another. Once again, the motivation comes from finite sets. Note that. So, yeah, we'll continue in our next discussion. Right, I think that it was awesome having this discussion right now. And we shall continue and look at more metric spaces, but also past exam questions on these particular sections. But yeah, very, very interesting discussion we had. But very elementary means we're still building up. But in our next meeting, I'm sure we shall reach metric spaces and the other things that you need to learn. At least as much as cardinality sometimes is examined, this one, it pops up. So it is very, very important that we have some understanding of these, but also that we're able to prove some results for assessment purposes. Right, it was awesome having this discussion this time around.